Did somebody say they're not ready? Oh, okay. All right, the equation, the determinant of a minus lambda I equals 0 is called what? The characteristic equation. Of A. Good. Two matrices A and B are called what if B equals P inverse AP for some matrix P? Similar, yeah. And a matrix A is called what if it can be written as PD P inverse? That is, it's similar to a diagonal matrix D. Diagonalizable. Diagonalizable. Yeah. It takes some practice to be able to say that word. So some notes on the reading. Just want to point out like a couple of key things before we do some examples that use it. So highlight some things. Okay. So to find the eigenvalues of a matrix, you're looking for all scalars lambda such that a minus lambda I times x equals 0 has a non-trivial solution, a non-zero solution. So last class we were given a lambda and asked, is it an eigenvalue? And you were able to plug in there and say, oh yeah, there's a non-trivial solution. Yeah, it's an eigenvalue. So today we're going to try to find eigenvalues. So this is how we find them. The invertible matrix theorem says that that equation has a non-trivial solution is equivalent to saying that a minus lambda I is not invertible, right? Because that is the null space of the matrix a minus lambda I. If that has a non-trivial solution, it's equivalent to saying a minus lambda I is not invertible. A minus lambda I not being invertible is equivalent to saying its determinant is 0. So that's why the characteristic equation is what it is. Finding the determinant of a minus lambda I and setting that equal to 0, that lets you find eigenvalues. Because the determinant is 0 means a minus lambda I is not invertible, means a minus lambda I times x equals 0 has non-trivial solution, which is the definition of the eigenvalue lambda. So we call that thing the characteristic equation. When you don't have the equals 0 part, we call it the characteristic polynomial. And then eigenvalues can have multiplicity, like just like zeros of a polynomial can have multiplicity. And it works exactly the same way because you're solving a polynomial equals 0. So if the 0 has a multiplicity, you say the eigenvalue has a multiplicity. So in the process of finding eigenvalues, you're going to need to know some stuff about determinants, like how to find determinants, because that's how you find them. You set the determinant of something equal to 0. So I'll remind you as we go how to find certain techniques for finding determinants. And then something to add to the invertible matrix theorem is that if you have an eigenvalue of 0, your matrix is not invertible. And then we have some stuff about similarity. A is similar to B if you can write B as P inverse AP for some matrix P. If A and B are similar, then they have the same eigenvalues. And then the dimension of the eigenspace is always less than or equal to the multiplicity of the lambda. Yeah.
I was a little confused by that determinant A.
Oh, yeah, yeah. Okay.
So is it the R is the number of row interchanges? So
yep.
Is it literally number 1 to like 4, the negative 1 to 4?
Yeah.
Okay.
Yeah. So if you
comes out negative, or sorry,
an
odd number goes to a value.
Yes. Yeah. So each time you interchange rows, that changes the sign of the determinant. So this is just a way of capturing that in one line. Yeah.
Now that I understand it, because it would sometimes go positive, sometimes negative, like 4.
Right. Yeah. So if you interchange rows, that changes the sign. But then if you interchange rows again, changes the sign back. So that's just a way of explaining that in symbols. All right, so we'll do some examples how to find eigenvalues and without first being given an eigenvector. Okay, so get a 2 by 2 matrix. I want to find the characteristic polynomial. That is defined as the determinant of A minus lambda I. Okay. So lambda I is just, in this case, lambda 0, 0, lambda in the 2 by 2 case. Lambda times the identity matrix. So I'm going to do A minus lambda I and take its determinant. So -1 minus lambda, and then 1 and 4 don't change because those are -0, and then 2 minus lambda. So how do you take the determinant of a 2 by 2?
AB minus BC.
Close. AD minus BC. Yeah. So this is going to be -1 minus lambda, that's A, times D, 2 minus lambda, minus B times C, 4 times 1. So I'm just going to multiply this all out, combine my like terms and stuff. So I get -2 plus lambda minus 2 lambda is minus lambda plus lambda squared minus 4. Combine like terms, so I have lambda squared minus lambda plus minus 6. Whoa. Minus 6, there we go. This is the characteristic polynomial. Just the determinant of A minus lambda I. And then to find the eigenvalues, you set your characteristic polynomial equal to 0 and solve. So part B. Factor it, and you get lambda minus 3, lambda plus 2. So lambda comes out to be 3 and -2. Two eigenvalues, 3 and -2. So that's basically it. That's how you find eigenvalues. And then your activities are going to walk you through some other stuff. And we'll do 30 minutes or so, and then we'll do the start of the next lesson.